All right, let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1108. We had a lot of problems doing last time, so let's jump back into it. See where we were. Okay, screen is up. Make sure I can see the chat. Okay, there we go. So these are the notes from yesterday. So this is what we were trying to go through yesterday, these 4 problems. We got through like 2 of them because we did them in a bunch of different ways. So problem 1, just illustrating some of the ways that you could approach problem 1 if you wanted to, is you could actually do a table, right? You could immediately jump in, find the number of possible outcomes by the multiplication rule. Your number of rows would be equal to your number of outcomes, and the number of stages of the experiment equal to the number of columns. And we know, because there are 2 options, we can alternate all our elements every 2 to the I times, where I starts from 0, then goes to 1, then goes to 2. And that way you essentially you get all possible scenarios. You'll never miss one doing that. And so, yeah, you can fill out an entire table and you can see all possible situations right there, and you can just count the ones that you want. So we did that, and it was pretty easy after constructing the table, which took the most time. I even explained how to do it, but you wouldn't really have to do that if you're doing a problem. Answering the problems were easy because now you could just count the rows where the thing that you want happened, and you divide that by, 8. We could also do a tree diagram, where at this point you didn't even have to remember that you didn't even have to use the multiplication rule to figure out the number of situations. Just by you branching off the tree until you get to the end tells you how many situations there are. You end up with 8 at the end. And again, by counting the arms of the tree, we could figure out the probabilities, right? Another method was to use our method of just visualizing what's going on. I taught you a bunch of ways to visualize different probabilities. Find the size of the sample space via the multiplication rule, and then just use concepts, counting principles to find the number of things you want, right? So here we could use a combination. I taught you about combinations, permutations, other things with counting. And we could go through with that. Another one that we could have done, of course, which I'll talk about again with the next example, is enumerate. Enumerate just means counting like everyone else counts. 1, 2, 3. You list out all the possible things that you could want, right? So if A is the number of ways to get exactly 1 heads, there are only 3 coordinates that you could write out. If B is the way to get exactly 2 heads, there's only 3 coordinates you can write out. C was the way to get at most 2 heads. Its complement was a lot easier to write out. And so I wrote out that, and we could use that to find C. So again, by using the multiplication rule to find the denominator, we could do that. Yeah. Then we did the 2 dice problem. Several ways to do this, but I think the table way is a nice way to do it. So you pretty much drew the table, and then from the table, you could count out all the things that you wanted. We could also examine the probabilities from the table. This is something we're going to be doing later on, and draw a histogram, sort of where the mass of the probability is focused on. And that was pretty cool. We have to try these guys for next time, so that's where we are. Yeah. Okay, so 1, we did this. We did that to death, right? You don't have to know all the ways, just know a couple ways. And just do it the way that you like, essentially. Like, I don't really recommend one thing I did over the other. I just wanted to show you guys multiple ways to do the same thing. If any particular way confuses you, just forget about it and look at the other way, right? So with me teaching you like 4 methods to do this one problem, like you don't have to know all 4 methods, strictly speaking. But I would recommend that you know something that can deal with it when the situations get huge, right? Like if you have a very large sample space, you probably don't want to draw a tree diagram or a table in that scenario. But other than that, like I don't not recommend tables or anything like that. So we did number 1. We did number 4 as well. I want to do a little bit more on number 4. I want to show you the enumeration way of doing number 4, as well as a wrong way to do number 4 that a student might do thinking that they're following the rules, but they're not. Just guessing that you know what the answer is. That's, of course, we're beyond that, right? We did the probability teasers. We know that we cannot guess probabilities. They don't follow our intuition. So we're not even going to do that anymore, right? Like, yeah, we know that. Okay, good. I'm glad we agree. So when we're finding probabilities, we're going to stick to the rules. We're going to stick to the basics. What is my sample space? How big is it? What is the thing I want? How big is that? Divide these two numbers. You will never guess at a probability ever again. It's not, yeah, humans aren't good at doing this, right? And it's not just you guys, and it's not because you're not smart or anything like that. Like humans in general are bad at guessing probabilities, right? We'll talk about that a little bit more later on. So don't go into that. Oh, well, I feel like, oh, there are 2 red cards and there were 4 cards. I guess the probability is half. No, we do not do that anymore. You count very slowly. Okay, so we're going to do that, and we're going to do 2 more examples. Example 8, we do know enough to do example 8, and we are going to do it, but it's going to lead us to another concept, which we want to cover. Okay, so let's do example 4 again. And to that end, let's move some of these guys out the way. iPad doesn't like the making the insert space function. It's very complicated for Apple. Okay, so the 2 dice. Okay, so we saw one way to do this. Here's another. And the method is just enumeration. It's usually the most inefficient way to do a probability problem. But it works, and that's good enough sometimes, right? I'm not grading you for efficiency. I'm not like, oh, this dude took like 8 lines to do this problem and this other dude took 10, like this guy automatically gets more points. Like that's not how I grade. I don't grade by efficiency. As long as your efficiency allows you to finish the test on time, I'm cool with it. So just because the way is inefficient doesn't mean that you can't use it. Sometimes if you can't come up with some fancy, sophisticated answer, don't. Just jump in and just get your hands dirty, So that's what we're going to do. So if we look at A, whereas find the probability that you roll a sum of 7. So we already know here. So if S is the sample space, it's trickling in here. Then the size of S is going to be 6 times 6 equals 36 by multiplication rule. How do I know? Because that's the first die, that's the second die, and these are the choices We normally write the choice numbers in blue. Let's actually do that. Right, so we can know the total size of the sample space is 36 without even writing that out. So we can save ourselves some time there. So A, let A be the event. We get the sum of 7. Event, the sum is 7. Remember, this is just a set. So enumerate just means list every possible element one by one. Remember, events are sets. So now you can list all possible ways that you can get a sum of 7. The first die could be 1, and the second die could be 6. You can also go the other way, 6 and 1. Another way to get a 7, the first die could be 2, and the other one could be 5. And of course, you can go the other way, 5 and 2. Another way to get 7, well, one die could be 3, the other could be 4, or going the other way, 4 and 3. Any other thing? If I increase die 1 to 4, then die 2 would have to be 3, and I already have that. Increase die 1 to 5, die 2 would have to be 2, I already have that. Increase die 1 to 6, die 2 would have to be 1, I already have that. This is it, right? And so now this means the size of A is 6. This means that the probability of A is the size of A over the size of S. 6 over 36 equals 1/6. We got that already last time with the table, right? So this is another way you could have written it out. Student who did it this way would have gotten full credit, just like the student who drew the table. But of course, the table is more general here because I can draw one table and find all the answers. Here, if you're enumerating, it's a little bit less efficient because you'd have to kind of list everything out that you want. So moving to B, let B equals the event. Sum is even is what we wanted. So you look at B and you list them out. Now, how can you get an even? You should realize that if you add 2 evens or 2 odds, the result is even. Right? So if you add 2 even numbers and you add 2 odd numbers, the result is even. So you can just focus on doing that. Focus on adding only even numbers and only odd numbers. So look at only even numbers. So that could be 2 and 2, 2 and 4, 2 and 6. That's that's when die 1 is the smallest even number. But I could start bumping up die 1 to a bigger even number. So it can jump up to 4. And it would be 4 and 2, 4 and 4, 4 and 6. And die 1 can bump up to the next even number, 6, 6 and 2, 6 and 4, 6 and 6. Okay. Now I can go with the odds, right? The lowest for die 1 could be 1. And then for all the odds, it could be 1 and 1, 1 and 3, 1 and 5. Then it could bump up to 3, 3 and 1, 3 and 3, 3 and 5. Then it can bump up to 5, 5 and 1, 5 and 3, 5 and 5. And I think that's all of them. Now, how many is that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So this means that the size of B is 18. And so the probability of B is the size of B over the size of the sample space, 18 over 36, which is a half. Okay, so that's another way we could get through problem 4. And were there only 2 parts of problem 4? Okay, if you had to guess the sum of blah, 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 we'll skip C and D. But part C would probably be maybe hard with this method. Unless you pick up a pattern. Because there was a pattern, right? The numbers actually moved in a pattern. When I wrote them out, you probably saw it. Right? Probably of 2 was 1, then for 3 it went to 2, then for 4 it went to 3, then for 5 it went to 4. You notice that the number of ways you can get each sum is increasing. It increases all the way up to 7 and then starts decreasing. It's possible you could figure out that pattern by just writing out a few enumerations. Okay. Yeah. So here's something I also want to talk about. A wrong way to do problem 7. Problem 4. Okay, so this is not what you can do, but this is something that I think someone could reasonably come up with. So you could think, for example, so you can say, well, all possible sums are 2, like if I get 2 1s, 3 if I get a 2 and a 1, 4, etc. Goes all the way up to 12 if I got 2 6s. So we could set S to be all possibilities to be 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we can say that S is the set of all possible sums. And then we can get that, oh, the size of S would actually be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And then we can say, all right, so if A is event we get 7, then this means that your A would just be the set with the sum 7. And then this means that the size of A is 1. And this means that the probability of A would be the size of A over the size of S would be 1 over 11. But this is wrong, right? But notice that it kind of feels right, doesn't it? Does anyone see what is wrong here? Like if you were to do this, where did the mistake actually happen? It looks like we were following the procedure. Everything was going great. I paid attention in class. This seems to be what Jhevon does. Figures out the sample space. He counts the size of the sample space, takes his event, count the size of his event. Then he divides the numbers. What went wrong here? How much time do we have?
You didn't take into account the different ways to get the sums.
Right. So way back when did I even do this? When we were talking about how to get a probability, you want to create a sample space where you have equally likely events, meaning everything you write down, you want to know that they're all equally likely. What the problem was here is that The sample space was messed up. The sample space was not equally likely. Have equally likely sample points. The truth is, yeah, I wrote down the numbers 2, 3, 4, 5, 6, and 7, blah, blah, blah. I wrote them all down once, but the truth is, they're not all worth 1, right? Some of them have a heavier weight. This is a concept called probability measure. You would say each of these sample points have a different measure. But really, you don't have to really know about that concept. It's when you get to advanced probability, they'll talk about that concept. The idea is the 2, for example, could happen one way, right? Whereas something like the 7 could happen 6 ways, right? They're not the same. When I write them out in this list, it's like I'm equating the 2 and the 7. Oh, I just have to worry about getting a 2 and a 7. Well, no, there are way more ways to get the 7 than there is to get the 2, and etc. So these guys have different measure. And so you'd have to take that into account. So if you're going to write out the sample space this way, you'd have to have some other measure of how much each thing weighs. So you know that, okay, the 2 has a weight of 1, the 3 has a weight of 2, the 4 has a weight of 3, the 5 has a weight of 6, the 5 has a weight of 4, 6 has a weight of 5, the 7 has a weight of 6. So when you take that 7 counts for like 6 things in one. And it's not shown here by writing that in a set. So this would be a dangerous way to actually do the problem, I think. If you were taking into account measure while you're doing this, you could do it this way, but in general, you can't. Like the size of this sample space isn't just by the number of elements that I could write down, because the number of elements each have multiple ways to achieve. And so that kind of makes it bad. So this is also why I mentioned a couple classes ago that when it comes to creating the sample space or conceptualizing the sample space, creativity is needed. You need to make sure that your sample space covers all the bases. It should be something that captures the essence of the problem. The sample space I just wrote down didn't do that. So yeah. So that's a potential issue that can arise. And I wanted you guys to be aware of that. And yeah, all right, cool. So we also beat that problem to death. Okay, let's move down to problem 5. Did anyone get the answer for this? You got turned down for some reason. You have 4 playing cards, 2 are red and 2 are black. Xi Jing thinks it's 1/3, which he put in the chat there. How did you get that?
There's totally 3 possible outcomes.
Yeah, but how did you come up with that? What was your sample space or the size of your sample space? How did you figure that out?
It's like use combination. You you have 4 cards and you choose 2 from them.
Okay, so one way, I guess. There are of course multiple. So the S is going to be the set of all 2 card pairs, which you are thinking of as a set of sets. Is that correct? Because once you're using combination, that's what you're actually doing. So you're imagining that there's a first red and a second red, or there could be a first black and a second black, or I could choose one of the reds and one of the blacks, or right? And so when you're counting sets within a set, that uses combination. So this means that your size of the sample space is going to be 4 choose 2. Or something like that, right? And what do you get here? That's what you did here? Well, no, you kind of imagined it different. I was writing down one way that I was going to think about it. You just imagine that there are 4 cards. We want to pick 2. That's what you thought. And so you said that there were 6 ways. Is this what you did?
Yeah.
And then what?
And then only you choose the same color cards, like the first one is black and the third one is black, like 2 red cards. So there is only 2 possible outcomes.
All right, so choose the color. So there are 2 colors. Choose one. So this is going to be 2 choose 1, which is 2. And then you said this means the probability of the same color equals 2/6, which is 1/3. Yeah, that works. Wasn't the way I was going to show you, but that does work. Right? That follows the principles. You figure out the size of your sample, figure out how many ways you can get what you want, you divide them. Another way. And this is going to show a very important idea also. Another way is to just visualize S as a set of tuples. Okay, so you can say let S equals the set of red 1, red 2, or black 1, black 2, etc. All possible combinations of tuples, which are specifically pairs made from red 1, red 2, black 1, black 2, right? Think of all possible pairs. And so now you want to look at the size of the sample space. So that would be what, right? You're counting how many ways you can actually create this. So this is card 1, card 2, but you want no repeats, right? So this is going to actually be P of 4, 2. So that's going to be, you can choose, you have 4 choices for your first card. You only have 3 choices for the other one. So this sample space has a size of 12. And now you say, well, let A be the event we have the same color. Event we have same color. And you could actually just enumerate this. There won't be a lot of possibilities. You can get 2 reds. And you could have chosen them in either order. You can get 2 blacks. Because I'm thinking of tuples, I have to worry about order now. I could get the first red and then the second red, or the second red first and then the first red. Also black. And so this leaves you, this means that the size of A is 4. And so you can get the probability of A is the size of A over the size of S, which is 4 over 12, equals 1/3. So again, when I said that to create the sample space, keep losing this part. When I said to create the sample space, you have to be creative, I really meant it in the sense that there is no one sample space. There is no unique way to think about a probability problem. Just make sure you think about it a way where you can conceptualize all possibilities. You can have someone coming up with totally different ways to conceptualize a probability sample space. And you can both get the same answer. Because once you're just consistent with the way you're thinking about things, once the way you're thinking about things is comprehensive enough and you're consistent in thinking about things that way, you'll get the answer. You'll get a third. Another way, another student might look at this problem. Yet another way. So Xijing thought of this way, and it's fine to think of it that way. So you can just think of it that way and ignore the other 2 ways I'm saying, because it seems like you're thinking about this okay. Another way you could think about this is visualize S as a set of sets. Let's say it didn't make sense to someone that they should worry about the order, right? Like I'm just picking 2 cards. Does it really matter if I pick one first or one second? Like I don't think it should matter. So I'm not going to use a tuple. I'm going to use just sets, in which case you can think of it as a set of sets. So you have red 1, red 2. And this accounts for if I pick red 1 first or red 2 first, or the order doesn't matter to me. Or I can have a set of black 1 and black 2. Or I can have a set of red 1 and black 1. Or I can have a bunch of different things. So the size of S is going to be the number of ways to choose 2 objects from 4 objects, namely red 1, red 2, black 1, or black 2. So that's 4 choose 2. And then if A is the same color, you can do this a bunch of ways. Again, you could list them. 4 choose 2 is 6. Sorry. Now, when you look at same color, you just want the red 1 and the red 2, or you want the black 1 and the black 2. And you don't really care about the order, but that still leaves you with the size of A is 2. And so the probability of A is 2 over 6. Right, so the numbers are the same here. but visualizing it was different. So here you're kind of completely going by counting principles and keeping everything in your head and not really visualizing anything, which is fine if you can handle it. But a lot of you might just want to see some sort of visualization. It helps you to think. And these would be two very popular ways to do it. But the one thing I wanted to point out is that, as the above illustrate, there is no unique sample space. S may be envisioned multiple ways. This is fine as long as it is comprehensive and useful enough. Okay. An example of one that's not useful was the wrong way to do problem 4. Right? But in general, there's no like one way. As long as you conceptualize it in a way, some people might want to think of things in order. Okay, I'm going to think of it as me picking a card first and then second, in which case you're thinking tuples, and you should be able to visualize it as tuples because now you have a whole bunch of rules that go along with tuples, right? Permutations go with tuples, especially when you don't want to have repeats. Multiplication rule goes with tuples when you want to allow repeats. So you have all these strategies that can help you once you visualize it as tuples. If you visualize something as sets, combinations will help with that. And some version of the multiplication rule can also help you with the size of the set. But once you visualize something as a bunch of sets, then combinations immediately becomes the go-to strategy as opposed to permutations. So once you have a way to visualize your sample space, and I would probably mention that, the two main ways to visualize S is as a set of sets or tuples. There's a reason why I went through set theory and taught you about sets and tuples, because that's the very common way to visualize sample spaces. And you do sets if we don't care about order. Or repeats. And use tuples if we do care about order. Or repeats. All right, so that's essentially going to be it. So the idea is, do I want to think of it as me choosing cards in a certain order? I can choose the first red first and then the second red, or the second red first and then the first red. Or do I just want to think of it as just a set of sets? I'm grabbing 2 cards. I don't care what order I get them in. It's a set containing red 1 and red 2. I don't care which one came first, right? Combinations would go with that method. Permutations would go with this method. And you wouldn't mix the two, right? So once you visualize your sample space, you have to be consistent. You should either be using tuple, so if you visualize a bunch of tuples, you should be using permutations and the multiplication rule. If you visualize as a bunch of sets, you should be using combinations and maybe the multiplication rule, right? Multiplication rule can apply all over the place, depending on how you set things up. So that's important. Yeah, those are a lot of concepts there, but hopefully that helps you out. Like I said, you don't have to know everything or every method. Look at all the methods I do, whichever one speaks to you most, just do it that way all the time. Okay, so I am going to introduce a new concept to you guys by going through this problem very quickly. So hold on till you seat of your pants, kids. Well, I mean, it's not going to be that complicated what I'm going to do. I'm pretty much going to do enumeration, but we're going to be able to develop a formula based on that. You roll 2 fair 6-sided dice. Find the probability that the sum is 10, given that one of the dice showed a 6. This might remind you of the 2 girls problem, right? What is the probability of 2 girls? What is the probability of 2 girls if we know that the older one is a girl named Freuda, right? What is the probability of 2 girls if we know one of the girls were born on a Monday, right? You remember that? When we add a condition to our probabilities, that's what this is about, right? It's not just finding the probability that the sum is 10. We know the probability that the sum is 10. I mean, we did that last time. Probability the sum is 10 is 3 over 36. Here is a very different question. What is the probability that the sum is 10 if we know for a fact that one of the dice is a 6? It's actually not going to be 3 out of 36. So let's actually think about this. So let S be set of x, y such that x equals 1, 2, 3, 4, 5, 6. Should say or 6, and y equals 1, 2, 3, 4, 5, or 6. By multiplication rule, this is just creating a set of 2 tuples where I have 6 options for the first coordinate and 6 options for the second coordinate. So this is just going to be 6 squared. Is the size of S. Okay, so we kind of already knew that. All right, now here we're going to do 2 things. Suppose A is let A be the set, the event we sum to 10. Okay, so this means that A is going to look like, let me do this all at once. And let B be the event one of the dice is 6. Okay. Then what would A look like? Well, I could get a 4 and a 6. I could get a 6 and a 4. I could get a 5 and a 5. That's pretty much it, right? What would B look like? So what I do want you to notice is that the above is the general sample space, no restriction. Okay. But now we're getting to the restrictions, right? What if I was only reduced to the set of things where I get sixes? So the first one could be a 6, but the second one is something else. So it's 6 and 1, 6 and 2, 6 and 3, 6 and 4, 6 and 5, 6 and 6. Or the second one could be a 6, 1 and 6, 2 and 6, 3 and 6, 4 and 6, 5 and 6. 6 and 6 would be the same, right? And so here we have the size of S equals 36. We have the size of B equals 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And we have the size of A, which is 3. Okay, so we have all these guys. Okay. Now, what I want you to appreciate is that when they told us one of the numbers is 6, this actually changed the sample space on us, right? We saw that with the two girls where we had to throw away some of the coordinates. When told 1 is a 6, the sample space changed. It became B. So now, if we have the new sample space, right? And this would leave you with the new event we want. So what is the new event we want? At first, we wanted the sum to be 10, which we could get in 3 different ways, 4 and 6 or 6 and 4 or 5 and 5. Now, what happens? 5 and 5 is no longer an option. So I can now do 4 and 6 and 6 and 4, right? 5, 5 is no longer an option. Now, here's the crucial thing. What is this set? Okay, so I mean, look at all the sets that I have here. How would you describe the set 4, 6 and 6, 4 in terms of A and B? Because our S has kind of been taken out of play. So look at A and B and look at that set. How do you describe that set? Right, so the set 4, 6 and 6, 4, how does that relate to these two guys? Does anyone see? So this is why we did step operations. It's actually the intersection, right? We want the guys that are in A that are also in B. 5, 5 was not in B. So this is actually the intersection of the set. And so this means essentially the probability sum is 10 if 1 is 6 is going to be, well, the size of the thing we want over the size of the sample space, right? So this is what we want over new sample space. So how many things are in what we want? Well, there are 2 things. How many things were in B? 11 things. So it was 2 over 11. Now here's a thing. You don't want to have to construct sets and intersect them all the time. So we want to find a formula. So that formula is going to be, if I take A intersect B over B, what I can do is I can divide the top and the bottom by S. That's like multiplying by 1. And then what you'll notice about the top is, by definition, that is the probability of A intersect B. And by definition, the bottom is the probability of B. So this leads to what we call a conditional probability. The probability that A occurs given that B already occurs is, this is the symbol that we use, probability of A given B. That's how it's read. And the formula is find the probability of the intersection and divide by the probability of B. This is red probability of A given B. We'll do a lot more work next time. We'll do problems with this guy next time. And I might even list some problems here in the notes so that you guys can work ahead, but I'll do that later. So it turns out you can find this kind of thing where you're given a condition by just taking intersections. And that was the new concept of probability that we're learning today, the conditional probability. We're going to work a lot more with conditional probability next time, but for now we're way over time. So I am going to let you guys go. So yeah, we'll talk a lot about conditional probability and some other things next time, and I will see you therefore in the next one. Ciao.